All right, so for lab 4 this week, we are looking at, the lab is titled Momentum. It's actually conservation of energy and momentum. So we are hypothesizing the conservation of energy and momentum in the collision of steel ball bearings. So last spring, a group, and one of the groups took a marble, last spring a group made these various observations that Dr. Ford sent to you last Thursday. So they took a marble, ran down this ramp, and then it fell from here a distance h, and forward from there. Forward from there from the origin to I naught. They did that 5 times, and they got some dots that landed somewhere in here inside of I naught, inside this circle here. And then they took another marble, they put it on top of the support and ran the marble down. And the marble that ran down landed at I, and the marble that came off the support landed at T. I for impactor and T for target. And did that 5 times. I got some more dots inside of I, inside the circle for I, and inside of the circle for T. To do this, we're looking at the conservation of energy momentum. Energy is our kinetic energy. Kinetic energy being 1/2 mv square, and momentum being a vector equal to mass times velocity. So to get through this, we need our velocity. So we have a distance, a horizontal velocity, which is our distance here, a distance from the origin to I naught, I, and T, but we need a time. And to do that, we have h. So h is equal to 1/2 gt squared, which means that t is equal to the square root of 2h on g. H is given to you in centimeters, g is given to you in meters. It doesn't matter which, it matters that the units match. It doesn't matter which one. I recommend that you take all your given measurements in centimeters and convert those to meters, so that you end up with a meter, with an h in meters, and a g in as 9.8 meters per second squared. The meters would cancel, and you get a t. That's somewhere in the neighborhood of less than half a second, because we're falling off the table, and h is not that far up. It's less than a meter. T H G. So now we need our velocities. Velocity initial is the distance O naught to I naught, which has been given to you, divided by the time taken to do so. V1, which is distance, which is given by I, and divide that by T. That's terrible. Try that again. That's strange. I divided by T. Little t, there we go. And V2, which is T, the target distance, divided by the time. Now we have 3 velocities for representing this this distance here, V1, this V initial, and this V2. Now we do our kinetic energy. So our kinetic energy initial is given to be 1/2 mv initial squared. This mass is the mass of the marble, which is given to you in the documentation, is given to you in grams. If you leave this as grams and this is meters per second, you end up with a millijoule, which is going to be 1,000 times bigger than the correct answer. Well, then it'll be numerically 1,000 times bigger if you were to call it a joule. WebAssign will take your answer in millijoules, or you can give it to it in joules, and it'll be less than 1/100th of a joule. So because this marble is, it's not particularly heavy. So we have, and then we have a kinetic energy initial, and kinetic energy 1 final, being 1/2 mv1 square. Kinetic energy 2 final, being 1/2 mv2 square. And then so we need to know our final kinetic energy, which is the sum of those. Kinetic energy 1 final. That's terrible. Back it up just a bit. Kinetic energy 1 final plus kinetic energy 2 final. And from that, we will get a percent error for our kinetic energy. Then we have our momentum in the x direction. V initial defines the x-axis. So this is mv initial. Cosine of theta is defining the x-axis, so this is 0. Cosine of 0 is 1, so it doesn't matter what that is. So this is mv initial. There we go. Pix, there we are. Then we need a pfx1. That'd be mv final 1. Oop. I didn't label it that way. I labeled it as v1 over here. So that's mv1 cosine theta 1. And pfx2 being mv2 cosine theta 2, like so. So now I can add those together and get our pfx, pfx1 plus pfx2. And from that, we'll get another percent error, comparing this one to that one. And then piy, because again, this initial direction defines the x-axis, this is by definition 0. So we need a pfy1. If we use our cosine on x, that means we use sine over here, so we end up with an mv1 sine theta 1. And a pfy, that's a little bit off. pfy2 being mv2 sine theta 2. Technically there's absolute value signs on these. I don't bother because it's more writing. But if you were taking the difference of these, supposedly that would come out to be 0 if everything worked out right. And so we won't be adding these. So we won't be adding them because to do that will take a difference and you end up with 0. And so comparisons to 0 are somewhat problematic. So you compare these to each other, and from that you'll get another percent error. 1, 2, 3% errors. So then the last question, you are told that you have a percent uncertainty of 14%. What the previous group did was they measured the radius of these circles here and divided by the length of the line that they are attached to. And then in principle, they should have taken an average. I don't know exactly what they did. All I know for certain is what Dr. Ford has told you, which is that your uncertainty is 14%. You have 3%, that's terrible, try again. 3% errors. You may average them or compare them individually to this 14%. Either way, it doesn't particularly matter. You should get your same answer for this particular experiment. What they're basically asking you to do is compare your percent uncertainty to a percent error. The percent error, if the conservation of energy momentum is exact, should be 0. So what we're doing is we have, on 1D case, 1D example, we have a distribution, a measurement, with a mu displaced from 0, and a width of that measurement being sigma. And then you need to compare mu to sigma. I'm going to run out of space if I do that right there. Oops. So if your mu is larger than sigma, that means that mu is further away from 0 than your sigma is wide, which means that you have falsified the hypothesis. That's terrible. Try again. Hypothesis. There we go. The hypothesis of conservation of energy and or momentum. If mu is less than sigma, that means that you are closer, that your error is closer to 0 than your measurement is wide, which means you need D right here. You have failed to falsify the hypothesis. And failure to falsify the hypothesis is not necessarily a bad thing. As the conservation of energy and momentum is expected for this collision of marbles which do not particularly deform. If you were to do this in a car collision, those cars will absorb a significant amount of energy, and so your energy may not be conserved, and you may not have momentum. And depending on how much friction there is involved, you may also not conserve your momentum either. So it is not bad to fail to falsify the hypothesis, but it's not a judgment value to fail to falsify the hypothesis. In fact, that's actually a good thing. It means you have done the experiment well in this particular case. All right.